Ever wonder how Spotify seems to know your taste in music so well? Or how those targeted ads seem to pop up right when you're thinking about buying something?
Yeah, it's kind of spooky sometimes, right?
Totally. But behind it all is the power of prediction, using data to anticipate what we'll do next. And at the heart of many of these technologies is something called linear regression.
Exactly. Linear regression. It's all about finding the best fit line. A concept you probably remember from school, but trust me, it's way more interesting than it sounds. This seemingly simple idea underpins some really powerful applications in machine learning.
Okay, you've piqued my interest. But before we get too far ahead of ourselves, let's back up a bit. What exactly is linear regression?
Right, so at its core, linear regression is a type of supervised learning. Imagine a student with a textbook and a detailed answer key. They're learning from labeled data, already knowing the right answers.
So we're kind of giving our algorithm a sneak peek at the test beforehand.
Exactly. And with that labeled data, the algorithm can pick up on patterns, learn relationships. Also, it can make predictions when it encounters new data.
Makes sense. But within supervised learning, there are a bunch of different paths we could take, right? Where does linear regression fit into all of this?
Good question. In supervised learning, we have two main branches, classification and regression. Imagine you're building a spam filter for your email.
Trying to keep that inbox clean.
Exactly. And you want to determine if an email is spam or not spam. That's a classification problem, sorting things into categories.
Okay, got it. So where does linear regression come in?
Well, linear regression steps in when we want to predict a continuous value, not just a category. Think about something like predicting house prices, where the price can be any value within a certain range, not just expensive or cheap.
So instead of putting things into neat little boxes, we're trying to pinpoint a specific spot on a spectrum.
Exactly. And we do that by, you guessed it, finding the best fit line.
Okay, like from algebra class, but how does that work in the real world with tons of data?
Picture a scatter plot with data points all over the graph. Linear regression tries to draw a straight line through those points to minimize the distance between the line and each point.
So it's like finding the average trend in all that data.
You could say that. It's all about capturing the underlying relationship between what we're trying to predict, let's say house prices, and the factors that influence it, like square footage or location.
And the closer those points cluster around the line, the more accurate our prediction should be.
Exactly right. That distance between each point and our line, that represents the error in our prediction. And the core of linear regression is minimizing those errors, finding that one line that best fits the data. And this is where we bump into an important concept, the cost function.
A cost function. Okay, that sounds kind of intimidating. Is that where we start penalizing the algorithm for making mistakes?
Not exactly. It's more like a judge at a baking competition, carefully evaluating how well each cake measures up to the ideal.
So in our case, the cost function is judging how well our line fits all those data points.
Exactly. And a really common cost function in linear regression is mean squared error, or MSE. It might sound complicated, but it's just a way to average out those square distances between our prediction line and the actual data points.
Okay, so our goal is to get a low score from the MSE judge, basically.
Exactly. The lower the score, the better our line fits the data, and the more accurate our predictions.
Makes sense. But how do we actually find that best fit line, that perfect recipe? How do we even begin to adjust it to get those errors down?
Well, that's where gradient descent comes in, kind of like a little algorithmic helper.
Or gradient descent. All right, I'm listening.
So imagine you're trying to find the lowest point in a valley, but you're blindfolded. You can feel the ground sloping downward, right? That's essentially what gradient descent does. It uses that slope to guide us toward the best solution.
Okay, so we're using the slope to guide us towards the lowest point, which means the smallest error.
Exactly. We want to reach the lowest point in our cost function because that means the smallest error. That gradient, that slope, tells us which way to adjust our line to move downhill toward that minimum. It's like taking small, careful steps down that hill until we reach the bottom.
So we're constantly making these tiny tweaks to the equation of our line, inching closer to the perfect fit with each step, guided by the gradient. This makes me think of that saying, practice makes perfect. But even with tons of practice, linear regression must have some limits, right? Like any good tool, it must have some rules.
You're absolutely right. Linear regression relies on certain assumptions about our data. And when those assumptions hold true, our model is more likely to give us accurate predictions.
But when they don't?
Let's just say Our results might be about as reliable as, I don't know, a weather forecast in the middle of a hurricane.
Okay, no pressure on our data then. So what are these assumptions? What do we need to keep an eye on?
Well, let's start with the most obvious one. Linearity. It's in the name after all. Linear regression works best when the relationship between the variables is, well, linear. Imagine trying to draw a straight line through a data set that looks like a parabola.
Yeah, that just doesn't seem like it'll work very well.
Not at all. It'd be like trying to fit a square peg in a round hole. So that's our first assumption.
Yeah.
Linearity. Our data needs to generally follow a straight line trend.
Okay, so linearity. Got it. What else?
Next up, independence. Each data point should be independent, meaning the value of one shouldn't affect the others.
Hmm. Okay, so like if we were trying to predict student test scores, but they were cheating off each other, those data points wouldn't be truly independent, right?
Yeah, that would definitely throw things off.
So we've got linearity, independence, anything else?
We also have something called homoscedasticity.
Homos... Say that again.
Homoscedasticity. It's a mouthful, I know, but it's a simple idea. Basically, it means that the spread of those errors, the distance from the points to our line, should be relatively consistent across all our data.
So if our errors were like sprinkles on a cupcake, they should be spread out evenly, not all clumped up in one spot.
That's a great analogy. I like it. Okay, so we've got linearity, independence, and this nicely distributed sprinkle of errors, or homoscedasticity.
Uh-huh.
Anything else?
Don't tell me there's more.
One more big one. We also assume normality. This means those errors should be normally distributed, following that bell curve shape. If our errors have a wonky distribution, it might mean our model isn't the best fit.
Got it. So our errors should be well-behaved, not too wild. Now, you mentioned earlier that things can get even trickier when we have multiple things influencing what we're trying to predict.
Right, and that's where multicollinearity rears its head.
Multi-what now?
Multicollinearity. It's not as scary as it sounds. Let's say you're trying to predict a house's price using both its square footage and the number of rooms. Those two things are usually connected. A bigger house usually has more rooms, right?
Yeah, bigger.
This overlap makes it hard for our model to figure out which factor is really driving that relationship with the house price.
So it's like trying to figure out which spice makes a dish taste good, but the chef used all your favorites at once.
Exactly. And when we have this multicollinearity, it can make our model a little less reliable and a bit harder to interpret.
Okay, so multicollinearity, not our friend. So let's say we've built our model, we've got our assumptions straight, we're watching out for multicollinearity, but how do we know if it's actually any good? It's like sending a kid off to school. You hope they learn something, but you need a progress report.
You're exactly right. Just like a student, our linear regression model needs a way to evaluate its performance.
So how do we grade it?
Luckily, we've got a whole bunch of metrics to give us that progress report we need.
So how do we grade our model's progress report? What metrics are we looking at?
Well, we can start with an old friend, MSE, or mean squared error. Remember our baking competition judge?
Always.
MSE tells us how far off our predictions are, on average, from those actual data points.
Right, lower is better. Want to impress that judge.
Exactly, but sometimes there's a little more to the story. Imagine we're predicting something where even small errors are a big deal. Like think stock prices.
High stakes.
Exactly. That's where MAE comes in handy. Mean absolute error. Similar to MSE, but it's a bit less sensitive to those extreme outliers that can sometimes skew the results.
So MAE is taking a more balanced approach, not overreacting to one or two big mistakes.
Exactly. And then we have RMSE, root mean squared error. Think of it like MSE's more interpretable cousin, basically the square root of MSE, which brings it back to the same units as our original data.
Okay, so if we're predicting house prices in dollars, RMSE gives us the error in dollars, not squared dollars, which is a little tough to wrap your head around.
Exactly. Makes it much easier to grasp those real-world implications.
Yeah.
But, all those metrics we've talked about, they're focused on the errors themselves. What if we want a bigger picture view to see how well our model is really explaining what's happening in the data?
Yeah, it's like, is our model actually understanding the assignment or just memorizing the answer key?
That's a great way to put it. And this is where R-squared struts onto the stage. Think of it as measuring how much of the change in what we're trying to predict is actually explained by our model.
So a higher R-squared, that means our model is doing a good job explaining those patterns in the data.
Exactly. If our model was trying to predict your mood based on the weather, a high R-squared would suggest that sunshine really does make a difference.
Makes sense to me.
But we can even take it a step further with adjusted R-squared. It's like R-squared, But with a bonus, it considers how many variables our model is using.
So it's like Goldilocks, trying to find the just right model. Not too simple, not too complex.
You got it. Not too hot, not too cold. Now, even when our data generally plays nicely with those assumptions we discussed, sometimes our model gets a little too excited during training.
Excited how?
Well, it can start to memorize the data instead of truly learning those underlying patterns.
It's like that student who aces every pop quiz by memorizing, but then totally blanks on the final exam.
You nailed it. That's called overfitting, and it's a real problem in machine learning. We don't want our model to just parrot back the data it's seen before.
So how do we fix that?
Well, luckily we have tools for that, like regularization.
Regularization. It sounds like we're bringing in a referee to keep our model in check.
Exactly. Think of regularization techniques like lasso, ridge, and elastic net as adding a bit of a penalty for overly complex models. It encourages them to focus on the most important variables, the core concepts, and not get lost in the weeds.
So it's all about balance. We need our model to fit the data well, but also stay general enough to make good predictions on new data it hasn't seen before.
Absolutely. And what's amazing is that linear regression, even though it sounds deceptively simple, has its fingers in so many pies.
Really?
Oh, yeah. Predicting house prices, forecasting stock market trends, even helping with medical diagnoses. Linear regression is everywhere.
Wow, it really is incredible how this seemingly basic idea of best fit can have such a huge impact.
It is. It's a great example of how we can use these fundamental math concepts to unlock new insights, new possibilities in all sorts of fields.
So next time our listeners see a trend line on a graph, they'll have a whole new appreciation for what's going on behind the scenes. It's been a fascinating deep dive into linear regression, hasn't it?
It really has.
Yeah.
Until next time.